Hi everyone, I'm Margarita Castillo-Téllez. I'm from la Universidad Autónoma de Campeche. I'm presenting the influence of solar drying on antioxidant profile on moringa leaves. As an introduction, I'm going to explain the importance of drying. For many years, humans have used hundreds of species of plants to treat disease. These practices continue to these days. In Mexico, according to Secretaría de Salud, at least 90% of the population use medicinal plants. Drying is the most common method of preserving medicinal plants, but due to the high invest and energy cost, represents an elevated expense. It is necessary to adopt technologies that effectively reduce post-harvest losses through the application of appropriate processing and conservation methods. Moringa is a plant that has generated great interest in the recent years because of its attributed medicinal properties. Moringa leaves analytical studies have identified as an important source of essential nutrients, rich in protein, essential amino acids, minerals, and vitamins. Solar energy is a good alternative for day-drying food because it can supply the energy needed from evaporated water from fruits, and plants, thus achieving an effective method of conservation. The drying of the moringa leaves is by direct exposure to the sun or in ovens. It is important to mention that in the international scientific literature, there are very few published studies on the solar drying of moringa leaves. The experimental study in this work, the drying process of moringa leaves in a direct solar dry cabinet type, open sun and non-convective oven at controlled temperature is analyzed experimentally. To determine if there was any effect due to the type of drying of the content of beneficial compounds, the antioxidant activity of the drying samples was determined using DPPH and ABTS techniques. The objective of determining the optimal condition of the drying process and compare the conventional, traditional, and solar, evaluating the possibility of integrating solar drying in sustainable agriculture and the adoption of this technology in Mexican households. Now we have here the solar drying technologies that we used in this experimental study. In the left side, we see the cabinet solar dryer, and in the right side, we see all the samples that we obtain at the end of the process, the natural convection, open sun, and forced convection. Now we have here some of the materials and instruments that we use to evaluate the different properties of moringa leaves before and after the processes. For the results, we obtain different types of graphics. One of them, in the left side, represents the solar irradiance, ambient temperature, and the relative humidity one day during the test period. On the right side, we can also see the variation in solar irradiance and temperature inside the drying chamber in DSE and open sun. We also can see the highest temperature we can obtain during the experimental test. Here we obtain the graphic that represents the variation in moisture content under open sun and cabinet dryer, and the drying rate as function of moisture content under open sun and cabinet dryer. We can easily see the difference between the three technologies that we use in the experimental study. Additionally, as you can see, we obtain the variation of moisture content respecting the drying time and the variation of drying rate depending on moisture content under controlled conditions at 45 and 55 Celsius degrees in the electric dryer. Finally, we obtain the quantifications of antioxidant activity of extract of moringa for each sample with the radical scavenger capacity, DPPH, and ABTS technique respectively. For the conclusions, we can say the kinetics of drying under controlled conditions show degradation times of 8.5 and 6 hours on average. At 45 and 55 Celsius degrees respectively, the optimum being 55 Celsius degrees. The drying times obtained in the cabinet solar dryer were shorter, 8 hours and 10 hours in the open on average. The drying times in the direct solar dryers under forced convection mode were well below the best oven drying times, with 55 Celsius degrees. The drying times in the open zone were very slow. It is a process that does not guarantee the final quality of the product, and it is not possible to control the measurement parameter of the solar drying. The antioxidant activity does correlate with the drying temperature. The best antioxidant activity was by forced convection, which had a constant temperature of 40 to 45 Celsius degrees. The open zone drying that had 34 to 35 Celsius degrees, but the drying process is very long. And the drying method that had the lowest antioxidant activity was natural convection, with a temperature range between 45 to 55 Celsius degrees. Antioxidant activity does correlate with the drying temperature. The best antioxidant activity was by forced convection, which had a constant temperature of 40 to 45 Celsius degrees, reaching up to 65 Celsius degrees. Perhaps this higher temperature slightly affects the antioxidant compounds.